Okay, so part 2 here. We're back to the shear diagram. We've seen how the shear diagram is a slope line for the uniform part of the load where it's all the same 650 pounds per foot, and that transfers down. But then there's a vertical point load at 6 feet away from the end there that we are trying to find what this distance is basically underneath there. So as we're looking at this shear part of the beam, what we're trying to find is what is that weight going to look like as a moment diagram. So we talked about the internal shear points. We're trying to figure out where does the shear of that point come over here. So we know that it's 6 feet to the point load. We're trying to figure out where does this X occur. Okay, so we're going to follow, let me look here. So what we're going to do is draw this moment diagram based off of what we actually see for the shear diagram up here. The moment diagram is going to be like a parabola looking thing, kind of a curved top. And so for pinned and roller connections, we know that there's no moment reaction. Therefore, the moment at pinned roller connection is 0. All right. So that is the X direction. We're not seeing any kind of reaction forces this way, so we're only looking at vertical reaction forces up and down. Okay. The moment diagram for a beam that has a uniform load is essentially parabolic. When the concentrated load is applied, hold on, lost my place there. When a concentrated load is composed of a straight line, the slope of the line is equal to the magnitude. And so what we're going to do is we need to know the distance of X in order to determine where the maximum moment will occur. Basically the point where the bending forces are the greatest. Because we know that the shear at 6 feet from the left end of the beam is 1,400 pounds, which is this lower remaining weight here. Okay, so the way that we're finding this out is that for 6 feet worth of distance, we have 650 pounds times 6, that's 3,900 pounds. Okay, and we start with 93. So 39 minus 93 minus an additional 4,000 leaves us with 1,400 pounds left. Okay, so on point A, on the far left-hand side, that connection is holding up 9,300 pounds. Okay, 6 feet of that is a uniform load of 650 pounds. So we take 6 feet times 650, we end up with 3,900. Then we also know that at 6 feet is 4,000 pounds pushing down. That's right there at the vertical section. So we take 39 plus 4,000 and subtract that from the 93, and what we end up with is that 1,400 pounds that's left over. Okay, everybody with me on that point? So we can find X by determining how much length is required in order for the 650 pounds per foot uniform load to counteract that 1,400 foot-pound force. So when we do that, we are left with 2.15 feet. Okay, so in the X section there, that's 6 foot to here, that remaining 1,400 pounds over 650 feet, 650 pounds per foot leaves us with 2.15 feet left over. So it's 8.15 feet over to the shear point, to the maximum force on that beam. All right? So now we can determine the maximum moment by finding the moment induced by all of the forces to the left of the point of zero shear. So that point of zero shear is that where they cross over, right? Like I have drawn up there. So what happens is that there's this slight kink in the line from here to here because it's kind of like a straight line point right to this thing. but this is that moment diagram where we see that it's at this point, not exactly in the middle, not the middle of 20 feet being 10 feet right dead center, but to the left of that, 8.15 feet, that's where we have our maximum moment, right? That comes into play when we start looking at all sorts of beams. When we actually pick steel, we need to find the maximum moment for our steel. So when we find this maximum moment, and again, there's a little kink in the curve there, now we need to figure out how much weight is on the beam at that point. Like, what's the force that's on that thing? So now we have to, at this point P, not necessarily the load location, but the point over here, this is the maximum moment. That's where the summing of the moments induced by the forces is acting to the left of this point. So we're going to sketch a free body diagram for the portion of the beam to the left of the point of zero shear, then sum the moments about this point. M represents the moment at this point required to resist the forces. So remembering that counterclockwise about point P is positive. So let's just hit pause for a second and we'll talk about, we'll get all of this thing sort of lined up. Okay? All right. So you see this equation over here, the big funny looking E with the MP equals 0. Okay? Anybody know from the summation, what's that actual symbol called right there? Anybody know? Sigma. Okay? That's an uppercase sigma. So the summation, the sum of all the moments about P must equal 0. The sum of all moments about P must equal 0. So let's look at the numbers that are listed down below there. M is a moment that we are trying to find out. That's the maximum moment that we are trying to find out. And that's just another one of the moments, because that's the sum of all the moments. Right? So the sum of the moment that we don't know just yet, plus 4,000 pounds at 2.15 feet. Okay? So we're basically taking this little section, 4,000 pounds at 2.15 feet. That's a moment. We're adding that to 650 pounds over 8.15 feet, because that's the entirety of this thing. So 8.15 feet total here. That's that one in the middle. Times 8.15 feet divided by 2, because you are splitting this up. And then minus the 4,000, minus the 9,300 at 8.15 feet, because that's the moment in the other direction. That's this side being positive, so that's like the twisting force going the other way. So we have one twisting force going this way. That's the 9,300 times 8.15 feet. That's this twisting force going that way. All of that stuff equals 0. Okay? So by the time that you either type this into your calculator or actually do the algebra and get the variable that we don't know onto one side and all the rest of the equation onto the other side, what we end up with is a number of that M that we don't know, that moment out here, the twisting force in this direction, in the positive direction this way, to counteract all the rest of the forces that we have on it, is 45,608 foot-pounds of torque, of twisting force. So that means that on that steel beam, in real life, if this was a floor that we were designing, that steel beam at the middle of it has a twisting force of 45,000 pounds per foot, trying to twist on it. Now you sort of get a feeling for how strong steel really is, so how strong steel I-beams really are. So, with all that being said, that gets us our final number for underneath here at 45,608. Okay? Now, what I like about this is that there's another way to do it. And I think that the other way to do it is maybe a little bit easier. Because for me, maybe it's a little bit more visual. But we are trying to find the maximum moment by basically adding up all of the moments that we had on the left side of this shear diagram. So everything from this point over, from the x equals 2.15 over to the left of that, we're trying to add all that stuff up. So if you just break this down into the shapes of area A, area B, and area C, you see them up here, A, B, and this tiny little triangle C. If you add all of them up, you get the maximum moment underneath here. So you get that same number. So if you take a look at that, it's just some pretty simple geometry, right? 1/2 of 6 feet times 3,900 pounds. So remember that this direction, the vertical direction, is the number of pounds, and in the horizontal direction is the number of feet. So if we take 6 times 39, that would be this entire square, but to find the area of a triangle, you divide that by half. So that's the area of A, plus the area of B, which is an actual 6-foot span left to right, times 5,400 pounds, because that's 4,000 plus 1,400. That's the total block there in B, the total block here. And then multiply or add that to your little tiny rectangle, or tiny little triangle at C here, which is only 2.15 feet in this direction and 1,400 pounds tall. So you take all of those, multiply them together, add them together, and you end up with 45,605. So the difference being 3 foot-pounds. That's 45,608. And this one is 45,605, which, when you're talking about 45,000 pounds, 3 pounds is not going to make a big difference, right? So that's, again, I find that one to be a little bit simpler. It does require that you write everything out and you sort of know what you're looking at. It's not just numbers based, but I'm a little bit more of a visual learner, so this one sort of resonates with me a little bit more. Ethan?
The same would go for the other side, right? The other 14 feet?
Yeah.
Find the area of that triangle.
If we needed to find the moment over there, or you're saying like find the maximum moment. We only need to find the maximum moment, so we only need to find the left side has more weight on it, so that's the one we need to find where the thing is. Are you asking if we would take 77 times the 14 foot and figure out if that's the same area?
That's 53,600.
Yeah. So that's the moment force going the other direction. Yeah. So we're looking for just to the left of the side here. Okay. Now, the thing about this is that I'm going to talk to you about what you're seeing up here on the screen. This is a program that can do all this for you. Okay? So while it's like basically my job as a teacher is to torture you with learning how to do all these things so that then when the computer does it for you, you know what's happening. And to jump forward even one more step above that, I can tell you from experience that my brother, that's the architectural engineer, he almost never has to look at doing these type of diagrams, because mostly they will have a package that's all sort of built together. So basically, like, if you're building a building that has these characteristics and you plan on having a floor that holds this much load, we already have done the math and we know that it's just going to be this I-beam that you are going to want. And if there's ever any changes to it, it's his responsibility to make sure that this actually does work. But you'll see in the next unit, or the next activity, when we start actually planning out the sizes of beams, that there's so much leeway in there. Like, we're looking for a beam that has a maximum moment of 45,000 pounds. We might get a steel I-beam that the maximum moment is 10% more than that. And, there's absolutely no risk that it's going to shear off at that point. Or, like I said before, if we're building it for a school, that means that the safety factor goes up and it's like 3 times the amount. So we might have a beam that the shear size is like 100,000, just because we know that it's going to be so much more than what we actually need. Okay. So I'm going to pause the screencast here, and we're going to work on trying to figure out a simple beam with loading for 1,090 pounds per foot and a span of 18 feet. So we're going to basically go through these steps again. So we see that with the 1,090 and 18 feet, what happens is we end up with this shear and this moment diagram.